Okay, so hello again, welcome back. We're going to continue talking about probability, and I want to move away from that sort of theoretical probability that we just saw with cards and all that kind of stuff, and let's talk about a different kind of probability called the statistical or empirical probability. The difference here is that we're dealing with the direct results of an experiment that we've already sort of conducted, or the data that we've collected from a statistical experiment, as opposed to some theoretical idea about hypothetically tossing coins or whatever. And so, for example, let's suppose that I thought about my sample space as just being the sample that I've collected from my experiment. So here I have a sample of 87 actresses, and I've sorted them into a little table here. And so I can think about events as just being subsets of my sample. And if I think about it this way, then the probability that an event would occur could be thought of as just the frequency of that event. What's the size of this event divided by my total frequency, or the size of my sample space. And so what do I mean by that? Let me just clarify with an example. So let's suppose I said, well, let's imagine that you picked an actress at random from our sample. So we have 87 actresses here, and you're going to close your eyes and reach into a hat, and you're going to pull one of these 87 actresses out. What's the probability that you select somebody between the ages of 21 and 30? Well, if I think about it, I know I have 87 total actresses. My total frequency, or the size of my sample, this is the same as sample size, is 87. And what are the odds that I pick out somebody from this group? Well, if I have the same chance of picking anybody out of these 87 actresses, then it's reasonable to say that the frequency of that event, being 32, divided by 87, gives me the probability that an actress is between 21 and 30 in this particular experiment. So how do I conclude? I say that, well, I have a 37% chance of picking an actress who's between 21 and 30. And this is basically, like I said, just the relative frequency of this particular frequency class. And so, of course, if I'm trying to find any probability, the real way to think about it, any statistical or empirical probability, the real way to think about it is that I need to think about, if you give me some event, it really is still just a subset of my sample space. So I have my sample space, and any subset of this, in these examples, it corresponds nicely to frequency classes. But if I take the size of some sort of event, some subset of the sample space, and I divide by the sample space, that gives me an idea of probability. So for example, continuing on the same chart, if I look at my table here and I say, well, what's the probability if I picked an actress at random from this group that she would be less than 50 years old? Well, what would that mean? Again, if I think about myself as sort of putting all these actresses' names in a hat and closing my eyes and pulling one out, then what I'm asking is, what's the probability that I would pick somebody from this group when I did that? And so, well, probability always represents the number of ways that what you're trying to find the likelihood of can happen, divided by the number of ways that anything can happen. So in this case, there's 87 different possibilities when I pull that name out of a hat. I can get any one of these 87 numbers. I could list all these actresses by name on the bottom, and that would actually be my sample space, the old-fashioned way. And how many ways can I pick somebody who's under 50? Well, just take a look, right? To pick somebody who's under 50 means that I either pick someone from 21 to 30. There's 32 ways that could happen. From 31 to 40, another 32 names on that list. And there's 14 ways I could have picked somebody from 41 to 50. So if I add all three of these numbers up and divide by 87, it gives me 64, 74, 78 over 87, which gives me approximately 90% chance that my actress is under 50. And so what this leads me to is an idea called the law of large numbers in probability. And we'll just try to get a good intuitive grasp of this thing. So notice that if I conduct an experiment, oftentimes, like to take an illustrative example, we can think of something like drawing cards, where it's very easy to see both the theoretical and statistical probabilities simultaneously. And so if I conduct an experiment, because of the nature of chance, then what I would expect is my viewed observations, or my statistical probability, to differ from the theoretical probability. So for example, down here is a table that represents me drawing 2 cards from a deck with replacement, putting the card back in, 100 times. And I kept track, remember we did this already, and there were 16 possible outcomes. And I kept track of how many times I drew each combination of suits. And so I drew hearts and then hearts 8 out of 100 times. I drew clubs and then diamonds 10 out of 100 times. And I drew hearts and then spades only 4 times. And so notice that none of these really represent the theoretical probability. We said that the theoretical probability of drawing any 2 suits, we actually only talked about hearts, hearts. And so what this leads us to is an important idea in statistics. It's called the law of large numbers. And so let's take an example here, drawing cards. And it's a nice example because it allows us to sort of simultaneously see statistical probabilities and theoretical probabilities. And this is real results. So what I did is I went online and I had an online card drawing generator thing, randomly pick 2 cards from a deck 100 times for me, with replacement, so putting the card back in. And it recorded the outcome. So here you can say that I drew hearts twice, 8 out of 100 times. For example, I drew clubs and then diamonds 10 out of 100 times. I drew, let's see, spades and then clubs 4 out of 100 times, and so on, and so on. And if you remember back, we've already looked at the theoretical example where we said the probability of drawing something like hearts twice was equal to 1 out of 16, because there's 16 possible outcomes. They all have the same theoretical likelihood of happening. And so our probability, 1 out of 16, comes to about 6.25%. But if I look at my statistical probability here, I had 100 experiment trials, and 8 times it actually came out as hearts, which gives me a statistical probability of 8% of drawing 2 hearts. And of course, the important point is that these numbers do not match. We don't expect that our results of our experiments will perfectly emulate our theoretical likelihood of these things happening. And that's just because there's chance involved. If I draw cards 100 times, then there's bound to be some variation. Just by luck and chance, I happen to draw, say, clubs and then diamonds much more frequently than hearts and then spades. So, what we can say, however, is that the more times I repeat my experiment, the closer and closer I expect my observed or statistical probabilities to approach these theoretical values. And what I mean by that is, let's suppose that I conducted this experiment more than 100 times. Let's suppose I conducted it 1,000 times. I wouldn't expect these results to stay in the same proportion they are now. If I did this, let's go even bigger. Let's say I did it 10,000 times. I wouldn't expect to see something like still only 400 or 4% of the time drawing hearts and spades, while drawing clubs and diamonds, 10% of the time. That's not what I would expect to see. I would expect to see all of these numbers to sort of converge in on about 6.25%. The more and more times I would repeat this experiment, these numbers would all even out to about the same frequency. You wouldn't expect, unless my deck had some kind of bias or these weren't truly all equal possibilities, I would never expect just this number to just somehow be occurring more frequently than any other number. And so one more example of this, just before I state the law of large numbers, is another example, a fun example I do in class, comes from this famous sort of Monty Hall problem. So just to quickly explain it to you, you can look into this yourself, but Let's Make a Deal was an old game show hosted by Monty Hall. And what he would do is he would give the contestant a choice of one of 3 doors. And behind one door there was some great prize, like a trip or a car. And behind the other 2 doors were just goats, as you can see with this picture. And so the contestant would pick which door he thought the car was behind. And after he made his choice, Monty would reveal one of the two remaining doors to have a goat. And then you would ask the contestant, do you want to keep your original door or do you want to switch? So the contestant would be faced with the choice. Let's say he originally picked door 3, and then Monty said, well, there's a goat behind door number 1, so you don't want that door. So do you want to switch to 2 or do you want to stay with 3? And so we can ask ourselves questions like, what is the probability that the contestant will win if he keeps his original door? And similarly, what is the probability that he will win if he decides to switch doors? And so there is a theoretical answer to what these probabilities are. But just for an illustration of the law of large numbers, we can also look at the statistical probability and run this experiment over and over and over and over again. And so because it's such a famous problem, you can go to this website and they'll run the experiment for you time and time again. They'll give you a choice to stay or to switch, and they'll let you know if you win the big prize or if you get a goat. And I went online and I did this. I ran the experiment 3,000 times, and for each occurrence. So when I had my contestant keep their choice of door, so remember, that means that they picked a door, like, say, door number 3, and then Monty said, well, it's not in door number 1, and they said, well, I want to stick with door number 3. Look how many times they won. Out of my 3,000 experiments, they won 978 times, and they lost 2,022 times. And so what that means is that they won 32.6% of the time and lost 67.4% of the time. Now, in comparison, say that contestant picked door number 3 to start, and then Monty said, oh, there's a goat behind door number 1. And then he said, do you want to switch doors? And they said, yes, let me switch to door number 2. Look what happened. They actually won 67% of the time and lost 33% of the time. And so, because we repeated this many, many times, this gives us a hint as to what actually those theoretical probabilities are. It makes sense to say that in this case, the statistical probability of winning looks like it's about, 32, 33%. But in this case over here, the probability of winning is actually 67 or so percent. And it's actually true. You can see this theoretical probability that it's actually, you have a twice as good a chance. You have a 2/3 chance of winning if you switch doors and only a 1/3 chance of winning if you stick with your original door. And so this shows us what we mean by the law of large numbers, and that as I repeat an experiment over and over and over again, if I would have done just 3 or 4 times, then I wouldn't have witnessed such overwhelmingly accurate statistical probabilities. I might have had some numbers here that were very misleading, and you can try this by running this experiment 3, 4, 5, 6, even 10 times and see how often you win. Just by getting lucky, you might win more than you should, or you might lose more than you should. But in the long run, the law of large numbers says that as we repeat these procedures over and over, our empirical or statistical probabilities converge in on what those theoretical probabilities really are. And so the bottom line is that, and this is the important concept, when you find your statistical probabilities, when you take your data and you assess a probability out of it, you should be thinking about this as an approximation of the theoretical probability. And the theoretical probability may be impossible to actually find. So if you find that there's a 60% chance that your people in your survey are between this range and this range, it's just an approximation of what sort of that real theoretical probability might actually be. And as you take a greater and greater number of observations, as your sample size increases, you're getting closer and closer and closer to what that real theoretical probability would be. That's it for now. We'll talk more about probability next.